Okay, so we are going to look at an example of rotational kinematics, and I'm going to date myself a little bit here. Imagine that you have a CD player. So before, MP3 players and phones and downloads, we actually used to play music on a CD. Actually, when I grew up, we used to play music on a tape. But CDs, they also used to be used for data storage in computers. But they were little discs, and they would spin. And how the data was encoded on that disc was read by a laser. And so underneath the disc, a laser would be reading the encoding on the grooves on the disc. And as the disc played, as it spun, the laser would move from the inside of the disc to the outside of the disc as it read the data on that disc. Well, there were some really important key features about how it read. First of all, that laser needed to read data at a steady rate. It read data at 1.3 meters per second is what the speed of the disc had to be going at the point that laser was under it in order for it to read it accurately. So at any point along the disc, the tangential speed had to be 1.3 meters per second. Now, the laser would move from the inside of the disc to the outside of the disc. So that had an influence over how the CD spun. How would it have to spin if the tangential velocity had to remain constant from the inside to the outside? Does it change? Well, yeah, it had to change. Let's just explore really quick conceptually before we get to the parts of the questions mathematically why that has to be the case. So imagine here's our disc. There's the center of the disc. And if the laser is directly under this point, then that point on the disc has to be spinning with a tangential velocity of 1.3 meters per second. And if my laser moves to a track later on the disc, further out on the disc, well, that point has to be spinning at 1.3 meters per second. Well, in order for this point on the disc to be spinning at 1.3 meters per second, like this point on the disc was spinning previously, well, this has to go farther. And so if they were spinning at the same rate, the outer disc, would be spinning faster. So as the laser moves from the inside to the outside, the disc has to slow down in its spinning. If it didn't slow down, then 1.3 meters per second at this point on the disc would be a lot slower than what this point in the disc was going. All right, so we know the disc has to slow down, so that's going to give us a clue into its angular acceleration, which is what we're going to want to look at later in the problem. So the first question in the problem asks, what's its angular speed on the inner track? On inner track, the disc is at 2.3 centimeters, or 23 millimeters, and what is its angular speed on an outer track, where it's sitting at 5.8 meters per second. So this is our rotational to translational, or translational to rotational motion. So we know, that for part A and B, we know that the angular speed is equal to the tangential velocity divided by the radius. Remember, the tangential speed is equal to omega times the radius. So a little bit of algebra gives me the relationship for the angular speed. So the angular speed at 2.3 centimeters is going to equal my 1.3 meters per second in meters, so 2.3 centimeters divided by 0.023. So that is my radius in meters. So 1.3 divided by 0.023, and I have my angular speed at 2.3 centimeters is equal to 56.5 radians per second. All right, so what is my angular speed at 5.3 centimeters? Well, I still need to be going 1.3 meters per second. 0.053 centimeters, so 1.3 divided by 0.053, I get 24.5 radians per second. All right, so at my lower radius and an inner track, I have to be going faster than when I'm at an outer track, which is exactly what we deduced. The disk has to slow down as it moves to an outer track, so it's spinning slower. Okay. Well, a CD on average plays for 73 minutes and 33 seconds. So they were, a good hour of jamming out to those CDs. If we do a conversion between 73 minutes and 33 seconds, I find that that's equal to 4,473 seconds. And go ahead and practice that conversion. So over that time, what is the angular acceleration of the disk? Well, this is a kinematics problem. So let's approach it like a kinematics problem. So we know that the object we're interested in is the disk spinning. We start to care at the inner track. We stop caring at the outer track. All right, so our list of variables is just like in our kinematics relationship, where we have initial and final position, radial position. We have initial and final angular velocity, and we have angular acceleration and time. So if we start at our initial, we don't know how many rotations it makes. That'll be part D. Our initial is at the inner track, so at 56.5 radians per second. Our final is at the outer track, 24.5 radians per second. We don't know our angular acceleration, but we know that the track runs for 4,473 seconds. So for part C, we are interested in what is this angular acceleration. Well, we can use our analogous kinematics equations for angular motion, or rotational motion, same thing, and we see that omega final angular velocity equals the initial angular velocity plus the acceleration, angular acceleration times time. My final angular velocity is 24.5, initial 56.5 plus theta or alpha times 4,473 seconds. All right, so 24.5 minus 56.5. We divide that by 4,473, and we get alpha being negative 7.15 times 10 to the minus 3 radians per second squared. Now, should it be negative? Well, yeah, because I made the assumption that it's going to be moving in a counterclockwise direction, positive direction. My initial was 0, so my final is going to be, my initial is positive, my final is smaller, moving in the positive direction, rotating in the positive direction. I'm slowing down, my acceleration and my speed have to be opposite. All right, so that is part C. And we are going to need that part C, 7.15 times 10 to the negative 3, for us to examine how many rotations does it make. Now, it's asking for how many rotations. And I'm still working in the world of radians, so I'm going to first go after what its final position radially is, how many angular displacement did it make, and then make that conversion to revolutions. All right, so we know that theta final is equal to a theta initial, omega initial times time, plus 1/2 alpha times squared. So again, our analogous kinematics equation. Theta final, we don't know. Theta initial is 0. Omega initial is 56.5 times 4473 plus 1/2 negative 7.13 e to the minus third times 4473 squared. And I hope we're in good calibration today. So 56.5 times 4473 is 252724.5 times negative 7.13 times 10 to the minus third times 4473 times 4473 minus 71327.6. So the difference is oops, I made a mistake. Okay, so 252724.5 minus 71327.6. We get 181396.9 radians. All right, so that's the number of radians that our object goes through. It's asking for the number of rotations or revolutions. So we have 181396.9 radians. And we know that there are 2 pi radians in 1 revolution. So if we divide that by 2 pi, we get 28870 rotations, or 2.89 times 10 to the 1, 2, 3, 4 rotations in the course of an entire disk playing its jams. All right, so looking at full kinematics here, not only the translation from linear motion to rotational motion in terms of how the angular velocity is related to the tangential velocity, but also then using our kinematics process, just like we did with one-dimensional motion and two-dimensional motion, to solve for this angular motion and obtaining the players of angular motion that we're interested in. So there's your example, a little bit dated, but it'll be historical someday, of angular kinematics. Good job.